We're going to be talking about polar coordinates. And a polar coordinate is very similar to a rectangular coordinate being a point x comma y. But polar coordinates are given as r comma theta, such that r is the radius or a length, and theta is an angle or a rotation. So there's some things to note here. First of all, there are no axes, just rotations with different lengths. So we can't say that given some coordinate plane, we have the point 2, 2. This does not work in polar coordinates. Instead, we would say we have some length r from the origin, so not drawn like this, but just to be clear, we're drawing some distance away from the origin, which I'll go ahead and put in red. And then we would rotate it some angle theta. And think about what happens when you rotate, you get a terminal side. So what ends up happening, I'm going to go ahead and undo this just to show the final thing. What ends up happening is we end up getting some length away from the origin with some angle theta, and this length is a distance of r, which ends up giving us our final point. The point ends up being r comma theta. So we can use this to connect the polar plane and the rectangular plane. Think about if we draw our rectangular plane, and then on top of it, we draw the polar plane. Well, what does the polar plane look like? It looks like a bunch of circles. Imagine if you took some radius or length r and made a bunch of complete rotations with it for all different types of lengths r. You would end up getting a circle that looks like this, another one that looks like this, another one that looks like this, and there'd be infinitely many of these, but you get the idea. So once we take all these circles and put them on our x and y axes, we overlay it, then if we want to find how to transfer a point from the polar plane to the rectangular plane, all we have to say is, where is this point on this circle in the rectangular plane? Let's just measure it up. And that's basically the idea. And we could do the same thing if we take this point in the rectangular plane. We could say, what circle does that point lie on? And at what angle? So these are how we can convert them, which is what this note says here. Just overlay the x and y axes on the polar plane. Okay, so with that in mind, we have a fact for our formulas that says, given that overlay that we just wrote, we know that x is equal to r cosine theta. So remember, whenever we dealt with triangles, we said x equals cosine theta. But that was for the unit circle when the radius was equal to 1. So what happens when the radius is equal to 2 or 3 or 4? Well, you just take cosine theta and multiply it by 2 or 3 or 4. And that still gives you your x value. All that's changed is the radius is no longer 1 times cosine theta. Sorry, not the radius, but the x value is no longer 1 times cosine theta. Now it's r times cosine theta. So whatever your r value is, multiply it by cosine of your angle, that gives you the x value. And you can probably guess that y would just be r times sine of theta. Instead of y equals sine theta for the unit circle, now we have r sine theta. And now to go from rectangular to polar. So this gives you x and y, the rectangular values, given the polar values. Now if you're given the rectangular values, you can get the polar values. And we get these by using the Pythagorean theorem. Given x and y, then x squared plus y squared equals r squared. And from there, given x and y also, we can use y divided by x equals tangent theta, and then take tangent inverse of each side to solve for theta. We just need to make note of what quadrant we're in, so we know what angle to pick. So now that we have all of our conversions, let's go ahead and try this out. We want to convert the square root of 2, 45 degrees to rectangular form. So we can start with x equals r cosine theta, so it equals the square root of 2 times cosine of 45 degrees. So we get the square root of 2 times cosine of 45 is the square root of 2 over 2. To multiply these, all we have to do is put the square root of 2 over 1 and multiply straight across, which gives us the square root of 2 times the square root of 2 is 2, over 1 times 2 is 2, which equals 1. So x equals 1. Now let's find y. So y equals r sine theta, which gives us the square root of 2 times sine of 45 degrees. And we know that sine of 45 degrees is also the square root of 2 over 2, which means we immediately know that this result will just be 1 as well. Y equals 1. So what is the rectangular form of the square root of 2, 45 degrees? It's x, y, which in this case is 1, 1. All right, so from here, we have a fact that says a polar point can be written in an infinite number of different forms. So just a quick way on how that could be true. Think about what happens if we have the point 2, 60 degrees and the point 2, 420 degrees. What do you notice about these 2 points? Well, they're a difference of 360 degrees apart, which means they are one complete rotation apart, meaning they lie on the exact same spot. They're the same point. They're just a rotation away from each other, but at the end of the day, that still represents the same point if you were to overlay it on the XY axes. So this polar point 2, 60 can be rewritten as 2, 420, and it still represents the same thing. Another way that we can rewrite these and still have the same value is we have a note that says given a negative r value, this is equivalent to a 180 degree rotation. So that one's a bit odd, but it's saying that if you had the point 2, well, let me make that negative, negative 2, 60, then if we change that negative 2 to a positive 2 and add or subtract 180 degrees from it, so let's say we add, we get 240 degrees. These 2 points are the same thing because a negative radius value just represents a flip of 180 degrees or a 180 degree rotation. So, for the following example, given 2, 30 degrees, we want to find 3 equivalent forms of this polar point. Take a moment, pause the video, see if you can't find 3. And just to be clear, there are an infinite number, so you may end up getting ones that I don't get, and so on. Okay, so trying this together, the first thing we can do is take 2, 30 and add 360 degrees to it. A very easy one. That would just give us 2, 390 degrees. So that one's already done. Now we need 2 more. Another thing we could do is make the 2 negative and add 180 degrees to the 30 degrees, which gives us 210 degrees. And finally, from there, we could take the regular 2 again, and then we could subtract 360 degrees from it, which gives us negative 330 degrees. And these are 3 equivalent forms of that polar point. Okay, so continuing on from here, we now want to convert 2, 60 degrees to rectangular form. So to convert this to rectangular form, I want you to take a moment, pause the video, see if you can't try to find this using the formulas we introduced a few moments ago. Okay, starting off with x, remember x equals r cosine theta, so we get 2 times cosine of 60 degrees, which gives us 2 times cosine of 60 is 1/2, which leaves us with x equals 1. 2 times 1/2, they're reciprocals, the result is 1. Now we have y equals 2 times sine of 60 degrees. Sine of 60 degrees is the square root of 3 over 2. So simplifying this, we can put this 2 over 1 and multiply. And when we do, notice we have a factor of 2 in the top and bottom that will cancel out, leaving us with the square root of 3 over 1, or just the square root of 3. So the rectangular form of 2, 60 degrees is 1, the square root of 3. So with that in mind, we now want to go ahead and work backwards. We want to convert 1, the square root of 3 to polar form. So to do this, remember we said r squared equals x squared plus y squared, our Pythagorean theorem, which gives us r squared equals 1 squared plus the square root of 3 squared. Simplifying, we get r squared equals 1 plus 3, which is just 4. So since r squared equals 4, we'll take the square root of each side to get r equals plus or minus the square root of 4, which is 2. Now, technically we could use either one here, but we're just going to go ahead and stick with the positive one. This way we don't have to worry about adding in that 180 degree flip. So now that we have the r value, let's find theta. And remember, theta we find with tangent theta equals y divided by x, which means tangent theta equals the square root of 3 over 1, which is just the square root of 3. And now with that, we need to get rid of tangent, so we'll take tangent inverse of each side of the equation, which gives us theta equals tangent inverse of the square root of 3 is 60 degrees. But before we just say, oh, well, the answer is 2 comma 60 degrees, circle the answer, and we're all set. Before we say that, we do have to make one quick check. And that is, we have to plot this coordinate. Always remember, when you go from rectangular to polar, you have to plot the point. And the reasoning is 1 comma the square root of 3, which is somewhere around here. This point is in quadrant 1. Because it's in quadrant 1, our angle works. 60 degrees is correct. But if we had plotted this point and it were in quadrant 3, we would have to make sure we choose an angle in quadrant 3, not 60 degrees, but for instance 240 degrees or something along those lines. So always make sure you check that you have the correct quadrant when you do this. Alright, now from here we're going to try a couple of problems of converting to the polar form from equations. So we want to find the polar equation of y equals x minus 3. And how can we do that? Well, when we find a polar equation, we're finding r in terms of theta. So we need to substitute r sine theta for y and r cosine theta for x. And then solve for r. So that gives us r sine theta equals r cosine theta minus 3. And how can we solve for r from here? Well, the trick is we need to get our r values together. So we're going to go ahead and subtract r cosine theta from each side of the equation. And when we do that, we get r sine theta minus r cosine theta equals negative 3. And from here, we can factor out an r because it's common between our two terms that are being subtracted, which gives us r times the quantity of sine theta minus cosine theta equals negative 3. And finally, we will divide each side of the equation by sine theta minus cosine theta, which gives us r equals negative 3 over sine theta minus cosine theta. And we could technically multiply the top and bottom by a negative 1 to get 3 over cosine theta minus sine theta to make it look a little bit nicer, but this is more than enough. We've converted the equation to its polar form. So this equation represents the same thing as this linear equation in rectangular form. Alright, so from there, we now want to find the polar form of y squared equals 9 minus x squared. Take a moment, pause the video, see if you can't do the same thing we just did in the previous problem. And there will be a little trick to this. Okay, so trying this together, y is r sine theta. So we get r sine theta quantity squared equals 9 minus x is r cosine theta quantity squared. So simplifying each of these square values, we get r squared sine squared theta equals 9 minus r squared cosine squared theta. we distribute the square to each of our terms because we're multiplying. And now we need to get our r's together just like last time, so we'll add r squared cosine squared theta to each side of the equation, which gives us r squared sine squared theta plus r squared cosine squared theta equals 9. And just like last time, we're going to factor out the common r squared in this case, not just r, but r squared, which gives us r squared times sine squared theta plus cosine squared theta equals 9. And now what do you notice about this? Well, hopefully you should see sine squared theta plus cosine squared theta is just 1. That's one of our Pythagorean identities. So we get r squared equals 9. And taking the square root of each side, we get r equals plus or minus 3. Either of these values, r equals 3 or r equals negative 3, represent the same polar form of y squared equals 9 minus x squared. And while it may not have been apparent what this equation represented, hopefully it's a little bit more apparent what this does. If not, it's totally fine. But imagine something that has a radius of 3 or a radius of negative 3. No matter what angle you have, that means you're just dealing with a circle with radius 3.